Hello everyone. Today we will discuss about photoelectric effect. In this lecture, we will focus on photoelectric effect discovery, its findings and application. So basically, photoelectric effect demonstrate light's interaction with matter. It occurs at the quantum level and it foundational to quantum mechanics and modern technology. This photoelectric effect, actually a very fundamental phenomenon of physics, reveals the dual nature of light behaving both as a wave and particle. First observed it in 19th century. This effect occurs when basically light shines on a metal surface and cause emission of electrons. While classical wave theory struggled to explain certain experimental results, it was Albert Einstein who in 1905 provided a revolutionary explanation by proposing that light is made up of discrete energy wave packet called photons. This idea not only explain observed behavior but also laid the foundation of quantum mechanics. So, photoelectric effect challenged long-standing nation about nature of light and led to profound changes in our understanding of energy, matter, and their interactions. Einstein work on this light photoelectric effect earned him that Nobel Prize, and he got the Nobel Prize in Physics in 1921. So in this lecture, basically we will cover the history of light, what are the nature of photoparticles, then the famous experiment of Leonard, in experimental investigation on that, and laws of photoelectric emissions, what are the failures of electromagnetics and classical physics. Then we will be focus on Einstein equation, experimental verifications, some applications. So let's begin understanding first that what happens when light strike on a metal surface. And before that, actually, when we show how Maxwell, Hertz, and other established firmly confirm that light is an electromagnetic wave, so that interference, diffraction, polarization demonstrate this wave nature of light. When we look more closely at the emission, absorption, and scattering of electromagnetic radiations, however, we discover a completely different aspect of light. We found that energy of an electromagnetic wave is quantized. It is emitted and absorbed in particle-like package of some definite energy as called by photons. So the energy of a single photon is basically proportional to frequency of radiation. So we will explore those. And light sometimes, as we said, that act as a waves and sometimes as particles. So how interference and diffraction demonstrate wave behavior, and other side the emission and absorption photon demonstrate the particle nature behavior. So whenever actually light or electromagnetic radiation like X-ray, ultraviolet ray falls on metal surface, it emit electron. So this process of emission of electron from metal surface, when illuminated by light of suitable wavelength, is called the photoelectric effect. So from when this came and how, so first let us look at the history of this light. So first in 1839, scientist Becquerel observed that initial effect observation on this effect, and then Hertz discovery, it came in 1887. Later on 1902, Linnart's investigations on photoelectric effect, and the complete explanation which we got, or which uh, we are now realizing or understanding all this effect, this Einstein explanation, it came on 1905. So basically, what type of materials is act for these photoelectrons on this, as we saying that metal light falls on the metal surface, so it could be any metal like zinc and cadmium, or any metal we can consider it. So first see that how, as we said, that light falls on the metal surface. So in this simple setup, that basically here this here this A and C, basically two plate, this A and C basically placed, and then it is actually in a evacuated quartz bulb, and light is falling on that one plate C. Then we can see that in this is one galvanometer, and E is connected as a battery. So when actually basically ultraviolet light incident on the plates, so we specify that here the plate A is the positive and C is the negative. So when it is falls on the negative plates only, the current flow in the circuit as indicated by galvanometer, but when light falls on the positive plate, this A, there is no current flow. So this observation confirms, or this observation shows that photoparticles must be negatively charged particle. So with this we can conclude that the photoparticle is the negatively charged particle. Now let's move to the Lennard's method. What is actually, Lennard's method, he calculated the electronic charge uh, and mass ratio. He calculated and he found out that if we know the experimentally the value finding, and shows that in various cases it is the same. So then discovered that photoparticles are nothing but they are the electrons. So in this setup basically, in this setup basically, it is consist of a glass tube G, and uh, which is evacuated through this T, and ultraviolet light we are passing through this terminal, and we are following the light in the C. C is the plate, and another side, this is another is P, and we can see that when basically here it is set in this way that that one side it is the earth counted, another side is, this is basically make it ground, and this U1 and E2 is these are basically connected to the electrodes, and P1 P2 are the small metal plate. P1 and P2 basically the small metal plate. So when the see here we get some negative potential and illuminated, then negatively charged particle are produced, and this whatever the charge is producing here, those will be accelerated towards the anode, and a few particle can pass through the hole. Here we can see a hole in this plate A anode. So a few will be passed, and they will go to the uniform velocity towards the P, this metal surface, and their arrival at P is basically will be indicated by here U1, and by if we apply now a uniform magnetic field, that which we have circled here in this part, actually this dotted line is here, this part. If we apply a magnetic field uniform, then what will happen that it will be, and we apply this magnetic field with the perpendicular to this plate. So and it direct and its direction is towards upward direction. The photoelectrons can be then deflected to P2 P2 plate here, and this arrival at the P2 plate will be will be uh, detected by this electron E2. So this is the actually full setup of this experiment, and then what his first observation is that here he basically want to demonstrate that the relation between the current and the applied potential in the C, means what the potential is applying here and the current which is flowing towards the whole system. So when the cathode potential basically several volts positive, the current was 0, and when V is supposed 2 volt, there are a very weak current source that a few particles pass through the velocity, overcome the retard potential 2 volt, and further if the potential further decrease, the current increases and reaches a saturation value for of about 20 volt. So basically, if we see this variation of the photoelectric current with the cathode potential, we can get a idea like that. Suppose this axis is the current, and we are plotting, and this axis the potential. So basically, if we just let us plot this side the negative and this side the positive. So suppose this is the this point is suppose plus 5, and if we see suppose so this is the minus 5, and so 10. So suppose let's say here the minus 15. So this V basically the potential of cathodes in unit of volt. So we can see that we can get, suppose here 2 volt, we can get a curve like that. So that if the potential further decreases, the current increases and becomes a saturated value for about in 20 volts. So this observation is helps to get the relation between that electronic charge and mass ratio with respect to the known parameters which are we are involving here, that applying the potential, getting the current and the magnetic field. So basically we can get a graph like that, and so this is basically, so if we just define the electronic charge is E and the potential is V, and small v is the this small v is basically the velocity of velocity of the photoelectrons, then we can find the relation of here actually the velocity imported by accelerating potential capital V is large, so that the velocity of the particle in the act of emission is negligible to compare to it. So if capital V is the capital V, suppose the accelerating potential, and small v is the velocity which is acquired by the photoelectron, then we can get the relation that half of mv square, the kinetic energy of the, if m is the mass of the photoelectrons, is equal to E in the potential EV. So now if we consider that what we have made that potential of magnetic field is a applying which is in a circle, and the radius of that circle is suppose r, and we are applying here the magnetic field B. So we can say that this photoelectron is is in the region of uniform magnetic field, then we can write that mv square divided by r is equal to mv square divided by r is equal to bev. So if we now this, suppose let's say this is equation 1 and this is equation 2. So from here we can find out the velocity v. So velocity v will be basically that b e r divided by m. So this is the velocity of the photoelectron. Now if we this from this equation, this v we have substitute here in equation over 1, then we can simply get E by m is equal to 2 v square r square. So this is our final equation from the Leonard's method. And what we can say from here, that if we know that potential, applied potential and the magnetic field and the r, ones can find out this E by m. So and he found that this E by m value is basically the same for that electrons, and it clearly shows that photoparticles are nothing but the electrons. So this was the main observation from this Leonard experiment, that the photoparticles are nothing but electron. So if we summarize this Leonard's method, that what was Leonard's proposal and what we achieved. So basically in this Leonard's experiment, that photoelectrons were ejected from the metal surface by lighting UV light, and kinetic energy of photoelectrons do not depend on the light intensity. Number of photoelectrons was proportional to the light intensity, and threshold frequency exists for each metal. So this is the main key information from the Leonard experiment. So now let us see the experimental investigation on photoelectric effect. So this is the basically the experimental photoelectric effect with the projected electron electroscope, and left. This is the experimental setup. So basically in this setup, I'll just overview it. That here it is on the photoelectric effect. Actually, if we want to study the photoelectric effect, it can be explained and can be studied simply from this setup. How that here this in this experiment, basically it consists in an evacuated glass tube. Suppose this orange one, this one is the evacuated tube T. Here have one window from where the light can pass, and this is the cathode plate, and this is the another plate, and here this um, that basically the photoelectric intensity of this plate is P, and C is a hollow cylinder, and it has a small hole from where actually light can pass towards the tube. And here a battery is connected, and this is the galvanometer G. And basically when the light from some source falls on the plate P, the photoelectrons are ejected, and they will ejected out from the plate. These photoelectrons are attracted by the positively charge of the cylinder C. Hence photoelectric current can flow from P to C in the bulb, where C to P outside the bulb. This current can be measured from the current detection that by this galvanometer, and it is found that the strength of this photoelectric current increases as the potential of C is more and more positive with respect to plate. So basically the deflection which we get in the G here galvanometer, The deflection is decreases when the potential of C is negative with respect to plate P. This deflection in G is decreases since when potential is negative with respect to P. Of this result obtained can be summarized in four statements basically, so which are known as the law of photoelectric emission. So this photoelectric, in very first it is says that for every metal there should be some minimum frequency of incident light below which there will be no photoelectric emission whatever be the intensity of the radiation. This minimum frequency which can cause the photoelectric emission is called the threshold frequency. So in single word we can say that for this photoelectron emission there should be the minimum frequency is the frequency of the threshold frequency. So minimum frequency required for photoelectric emission is the threshold frequency. Second is the strength of the photoelectric current. The strength of the photoelectric current is directly proportional to the intensity of the incident light, provided the frequency is greater than the threshold frequency. And third is the velocity, and hence the energy of the photoelectron is independent of incident of light. So photoelectron energy is independent of the intensity of light, but it depends on the frequency of the incident light and nature of the metal. So the velocity or energy of the photoelectron will be solely depends on the frequency of incident light and the nature of metal. And last one is the most important is the photoelectric emission is an instantaneous process. The time lag, if any, between incident of radiation and emission is never more than 3 into 10 power of minus 9 second. So we can share that this is very is the instantaneous process. So basically, main observation from law of emission is that at particular minimum frequency, photo emission will cause the photocurrent will be proportional to intensity of light, and energy of photoelectron will be depends on frequency and nature of the metal, and photoelectric emission is an instantaneous process. The time lag, if any, between incident of radiation and emission of electron is very less. So this was the observation, but there is some incidents in electromagnetic theory or classical theory which cannot explain from this experiment fact. So like that it cannot explain that calculation shows that it would require about 500 days to dislodge a photoelectron from a sodium exposure to violet light of wavelength 400 angstrom. But experimentally, however, we observe that electron eject comments without any delay. So this phenomena actually is not supporting the experiment, this observation or calculations. And also, according to the classical theory, basically the light of greater intensity shows impact greater kinetic energy than the liberated electrons, but this does not happen here. So the velocity of the emitted electron should not depends on the frequency of the incident light, but it does. So this phenomenon was however, this phenomenon is can explain very proper way in the basis of Planck's quantum theory of radiation. So what is that will come. So in short, what fails in classical physics. So classical physics failures is that wave theory contradiction is classical wave theory basically predicts the energy depends on the intensity. So this is direct contradictory from the experimental results on kinetic energy in particularly. And time delay problem that also mentioned means classical theory explains there has a time delay between electron emission at low intensity, but it does not hold true. And new framework like this failure of classical physics the new framework to explain the photoelectric effect. So the Planck's quantum theory of radiation basically it explained very nicely and very agreed way that the photoelectric effect. So the in short, what is the Planck's quantum theory? Basically, according to Planck, the energy of a monochromatic wave with frequency nu can if we assume that frequency nu can only assume those values with integer multiple like en is equal to n h nu where h is the Planck's constant. This h is the basically the Planck's constant. It is Planck's constant. And this n basically the integer value, this n basically the integer value referring to the number of photons. So in simpler, if there is the n number of photons, the total energy will be en h nu. So we can from here we can find out that energy of a single photon of frequency e is basically e is equal to h nu. So now let's see that what is the Einstein explanation. So basically Einstein explained first light as photon. Light consists of discrete energy packets known as photons. So basically when we are saying that amount of energy, that is basically a energy packet of photons means many photons energy togetherly. So in short it is kind of the discrete energy packets, and this energy photon energy proportional to the frequency. So energy of a single photon E is equal to h nu. E is equal to h nu, where h is the Planck's constant, nu is the frequency of the photon. And third is the quantum phenomenon. The photoelectric effect is fundamentally a quantum phenomenon. So this 3 point is that light as a photon, energy proportional to frequency and quantum phenomenon togetherly, combinedly give the Einstein thought or explanation about photoelectric effect. So this revolutionary explanation transforms physics. His works uh, basically gives that light made of with the photons with energy proportional to frequency. This insight define the complete photoelectric effect as a quantum phenomenon. So basically Einstein, let us see that Einstein's photoelectric emission. So according to Einstein, the light frequency nu consists of source of means a number of photons of energy h nu. So when basically the photon of light energy frequency light of frequency nu is incident on a metal, the energy is completely transformed to a free electrons of in the metal. A part of energy acquired by the electron basically used to pull out the electron from the surface surface of the metal, and rest of it utilized importing the kinetic energy to the emitted photon. So if it is divided in two part, basically that E is equal to h nu. So if suppose let first part, that phi, that first part, this phi is basically this phi, this is basically the energy spent in extracting the electron from the emitter to which it bound. So this is basically the we can say this is the photoelectric work function. So now this relation is basically called the Einstein photoelectric relation. Now let us consider that uh, is new naught is the threshold frequency for which frequency which just eject an electron from the metal without any velocity. Then we can write that phi is equal to h nu. Basically you can write phi is equal to h nu. If phi is equal to h nu, then our this Einstein photoelectric emission, this can be rewrite as h nu is equal to h nu naught plus half of mv max square. So here this v max is the velocity acquired by the electron. Or we can reframe this equation, half of mv max square is equal to basically h nu minus nu naught. So this equation basically gives the complete Einstein photoelectric effect emissions and the energy of the emitted photoelectron. So you can see that energy of that photoelectrons is independent of the intensity of the incident radiation, but decreases with the frequency. So basically we can define from here that the work function of the metal may be defined as that energy which is just sufficient to liberate electron from the metal surface with zero velocity. And this equation basically suggests us that energy of the emitted photoelectron is independent of the intensity of the incident radiation, but increases with the frequency. So basically Einstein equation is relating with the four parameters is energy, Planck's constant, frequency, and threshold frequency phi. So if we summarize it, so basically that is defined as the maximum kinetic energy of the emitted electron, that kinetic energy maximum. Next is the Planck's constant, that is the universal constant, and this Planck's constant value is 6.626 into 10 power of minus 34 joule second. And frequency nu, which is the frequency of the incident light, and the work function of the metal. It is very important for knowing photoelectric effect that in the what is the work function of the metal So as shared that this is nothing but the energy which is just sufficient to liberate electron from the metal surface with zero velocity. So we can conclude here that Einstein equation defines photoelectric effect, and here this phi is in simple way, this is the minimum energy to remove an electron. So now we'll verify this experimental verification of this Einstein photoelectric from the uh, Millikan's experiment. So basically it is the very famous experiments of Millikan's, and this is the Millikan. Actually he is a very great scientist that he first made the numerous discoveries in the field of electricity, optics, molecular physics. His earliest age, the earliest major success was the accurate determination of the charge carried by an electron using that elegant falling drop method. It was very one of famous experiment and well popular. He was also proved that this quantity was a constant for electron in 1910, and this demonstrating the atomic structure of the electricity. And next he verified the experimentally in the Einstein's all important photoelectric equations, and made the first dialectic determination of first direct photoelectric determination of Planck's constant H in 1912, 1915. So just briefly, that he precisely measured, confirmed the Einstein's equation, and determined the Planck's constant with very high accuracy, and also valid the quantum nature of light, and measure the work function of various materials. So basically he discovered in a very simple experiment that how this photoelectric emission can photoelectric effect equations of Einstein's is proved. So let us see that Millikan's experiment basically based that what is known as the stopping potential. So he actually used the stopping potential, which is the necessary retarding potential difference required in order to just hold the most of the energetic photoelectron emitted. So he used this stopping potential and then find out the relation. So basically that the total kinetic energy of the photoelectric photoelectron in the surface of the metal irradiated by light of frequency nu is basically half of mv square is h nu minus phi. So to prove this one, he just first define that V is, if capital V is the potential difference which is applied between the emitter and a collecting electrode, then basically the he defined basically the potential which is applying to the emitter and the collected electrode, and a collecting electrode actually in order to prevent the photoelectron just leaving the emitter. So the emitter being maintain a positive potential with respect to the collector. Then that EV is equal to half of mv max square, and this EV is basically we can write that h nu minus phi. So he find out from this equation that he calculated this potential V formula like V is equal to h by e nu minus phi by e, where phi is the constant for a given metal and h is the Planck's constant. So here we can see that this potential is only varying a formula with the frequency nu. So hence this equation 1 is represent. If we plot this one, actually basically if we plot one, that this is suppose y-axis and this is x-axis, and suppose this is y-axis. So if we plot this equation 1, we can represent like a straight line, like suppose this, and this is our this new knot, and this is our origin O. This is origin O. So basically here V is measured for different values of nu, and a graph, if we plot this graph in between stopping potential V and this axis, we are basically plotting the stopping potential V, and if we plot this x-axis, basically this is the frequency nu, and this is the threshold frequency nu naught, then we can get a graph like that. The slope of this straight line can be defined as tan theta is equal to h by e. Tan theta is equal to h by e. H is equal to e tan theta. So since here h is the Planck's constant, it can be calculated from this by knowing this theta value. So the intersection of this x-axis give the value of threshold frequency nu naught for a given emitter. From this photoelectric work function phi can be defined, phi is equal to h nu can be calculated. So if we know this, so we can get from here the phi is equal to basically this is, it will be basically Planck's constant h and then nu naught. So this experiment, basically he explained from this experiment, find out that light is passing through here, and then this is basically a evacuated tube, and this G is given, and see there are different from metal like lithium, sodium, potassium is given, and then here connecting light. This is the window or passage of light. So he basically find out, now he want to show here that the cylindrical this hold blocks, this sheet of the sodium, potassium, and the lithium are mounted on a spindle surface. Means it will be mount in the inside this with this glass flux G inside this glass, this complete tube, or you can say that glass flux. The flux is evacuated with a very high vacuum to free the metal from all absorbed gases and to prevent their oxidation. The spindle can be rotated just outside the electromagnet, and each metal block mm, rotates from outside by the electromagnet. So as each metal block passes by adjusting this by adjusting the sharp edge k, so a thin layer of it is, will be removed, thus exposing the fresh surface to the metal, irradiating light entering the flux through this quartz window here, and monochromatic light providing by this spectroscope, and it will be illuminate the fresh metal surface. So the whatever the photo electrons are collected by Faraday's cylinder F here, it will be whatever it will collect from this surface, that it will be basically the the cylinder is basically made of with the copper oxide. So copper oxide, so that if it is, since it is the copper oxide, it is not the photon sensitive. So the photocurrent is measured by this electromagnetic connected to this photocylinder. It will not affect here, and we can collect the fresh the photoelectron. So this was his experiment to observe the photoelectric effect. So basically he want to shown here that the stopping potential of these liberated photoelectrons is measured by raising the emitting surface with respect to a positive potential, and just sufficient to prevent any of the electrons from the to reach this collector surface F. To prevent that any of the electron can reaching here, he just put it this connection, these different metals, and made it rotating way. And basically here the stopping potential is nothing but the is the positive potential applied to the emitter, which is basically corresponds to the zero current in the electromagnet. And this stopping potential is determined for different wavelength of the incident light, and the value of basically the deterred potential capital V should be corrected by contacting the potential C, means potential C and this F, cylinder F. So that when we are plotting that we are getting the data from the potential with respect to the frequency, we will get this more accurate and a straight line graph. And if we find out that straight line graph, H by E can be easily obtained, which is nothing but the basically the H by E is equal to tan theta, and the substituting these values we can find out that E and H is calculated. So the value of H calculated in this way is very well agree or well accepted with the value obtained from the other method. So thus Einstein equation can be verified experimentally. So only using the stopping potential, or we can say the retarding potential, to verify the Einstein's whole photoelectric emissions. So just see that how very simple or easily you can find out the work function or the potential. Just one example. Suppose we want to find out the work function of the sodium in unit electron volt, and it is given that the threshold wavelength is this. So our given data here is that threshold wavelength is given and H is also here. So we know the only single equations of electromagnetic photoelectric effect of the Einstein's gives the formula for finding out the work function of the any of the metal. So this is basically, these three things is basically given. Planck's constant, C, we know that light velocity, and this is the mu naught, this is given here, the threshold frequency. So since we know the phi is basically h nu naught, hc by c, nu, basically we know that frequency nu is basically is equal to the, if lambda is the wavelength of light, so it is nothing but by c by lambda. So since we know this formula, and here it is nu naught and h and c is given, one can easily find out by incorporating all the values the work function of the metal. So basically for the case of sodium, if the wavelength is of this 6800, and we can get a work function of this 1.827 electron volt. So let us see the another that how to find out the kinetic energy of the electrons from this formula. It is also very easy to find out from here, that here it is given that photoelectric threshold for a metal is 3000 angstrom. Find the kinetic energy of the electron ejected from it by irradiated a wavelength of this. So here basically what are the things is given? Lambda is given, which is this. So let us change in the same unit, and lambda h and c, that is we know. So we know the kinetic energy formula is related with the phi naught and h nu. So the energy formula is kinetic energy of the electron half of mv square is basically is equal to h nu minus h nu naught. So here all these values is given. We can once can easily reformulate it in the since it is given the lambda, since we know that uh, nu is c by nu is equal to nu is basically nu is basically the c by lambda. So just reformulate this one and once can find out the kinetic energy of the electron. So just putting all these value once can find out the kinetic energy of the electron is 6.2 electron volt. So this was the beautiful and very nice explanation of the Einstein's about photoelectric effect and these equations. So in the our recent modern tech where we are using this photoelectric emission, photoelectric effect or those equation, and where we are, what we are doing with this, there are several basically applications of photoelectric effect, starting from the in it using the converting the solar energy to sunlight to the electricity in solar cell. It also used in photo detector devices. It used in the cameras. Many uses. These are the various applications. So applications of the modern tech. So it basically used as a light sensor. It can be used as light sensor. It can use in solar cell. Is this concept also? It is using very fastly used in medical imaging, and also another important is it is also used in the photo multiplier tubes. So basically this photoelectric effect powers our modern technology, starting from light sensor to photo multiplier tubes, and without whatever we are using in the modern age, various alternate ways on advanced lighting, or any of the sensitive experiment or sensitive tools we are using, or instruments we are using the photoelectric use concepts. So I'll just discuss about few photoelectric effects that one of the very most important is the photoelectric cells. So what is photoelectric cells? So photoelectric cell is but nothing but it is an arrangement of converting light energy into the electricity. So in physics, or we can say in the science, in the physical science, basically the cell is here we say that it is basically a arrangement where we is converting in photoelectric say the light energy into the electricity. So there are various type of photoelectric cells, like most importantly it is the emission photovoltaic, and photoconductive. It classified in three major things: photoemission, photovoltaics, and photoconductive. So, what are the photoemissive cells? So, this is the simple arrangement of photoemissive cell. So, photoemission basically it is consist with of a, you can see here that consists of a glass or a quartz bulb. So this setup is basically, and accordingly as it is used with the visible or ultraviolet light. So it mainly used for visible or ultraviolet light, and here basically the cathode, that is denoted here by C. In the cathode generally use the silver electrode, silver cathode, and in the form of you can see here that it is here, it is in the form of It is basically semi-cylindrical plate, and the anode that is here, this anode basically a rod that is mounted vertically at the center of the bulb, and it is parallel to its axis. So a positive potential of about suppose 100 volt is applied to the anode, and then the negative being connected to the cathode through the galvanometer G. And when actually light falls on the cathode, the electrons are ejected from the cathode, and a very small current flow through the cell, and that current which is flowing through the cell can be measured by this galvanometer G. So this photo emissive cell basically used for the reproduction of sound from the photofilms. So next is the photovoltaics. So this is the arrangement of the photovoltaics. Actually, photovoltaic cells, they have multiple layers. So suppose that middle layers is the semiconductor layer. So semiconductor layers where the actually basically light absorb, and also have the metal plate and surface film for the contact. And so most important component of the photovoltaic cell is the semiconductor layer, where basically the main light absorbed, and then electron hole produced and electron hole generated and then separated through the uh, electron transport layer and hole transport layer. So, and then once electron and hole separated and complete the circuit, we can connect here in a circuit, and we can measure the current in the output. So basically, as mentioned, that it consists of different layers, and in main important layer is the semiconductor layer. In one type of the photoelectric cell, basically the metal plate is made up with the copper and the semiconductor cuprous oxide Cu2O. So on the other side semiconductor, there is a very thin layer of we can say transparent layer, which allows the semiconductor to illuminate the radiation, so which is defined here. And actually light first fall on the surface, and surface of gold or silver penetrates into it and ejects photoelectron from semiconductor layer. This electron travels in the opposite direction, opposite to the direction of incident light, and then in conventional current therefore flow in the direction of the incident light. So for small value of resistance also added in the circuit, and the current will be directly proportional to the intensity of the light. So for this photovoltaic cell, actually we can see here that there are actually no batteries, no external battery is required to operate the photovoltaic cell, as the cell itself generate the EMF. And for the third, that is the photoconductive cell. Basically this is the photoconductive cells. So here basically based on the principle that the electrical resistance of semiconductor materials like selenium decreases with increasing the intensity of the radiation upon it, and the conductivity increases. So basically when a very small film of selenium is deposited on one side of the metal plate, let us say iron plate, and a potential difference 100 volt is applying, then iron and selenium both will form an electrical battery, and a galvanometer will be using here galvanometer will be using here to observe the deflection, and as the intensity of the light is varied, the resistance of the selenium also be varied accordingly, and the current of the circuit will be undergoes corresponding to that variation. So the basically the solar batteries consists of several thousand of photoconductive cells which produce kind of several kilowatt powers. So to specify the different three types of photo emission, photovoltaic and photoconductive cells, if we just split it, that photo emission cell basically used for reproducing of sound from photo films. Photovoltaic cell basically here that main unique thing is no external battery is used here, since the cell itself generates the EMF. And in the photoconductive cell, actually it basically used in the solar battery, which consists of basically the various photoconductive cell and which can give us the several kilowatts powers. So now if we conclude that these are the various photoelectric cells which uses the concept of photoelectric effect and gives their various applications. So basically it comes to the foundation of the quantum mechanics, that the particle we have discussed the particle nature of the light, the revolutionary understanding of this photoelectric effect, and we also discussed about the quantum mechanics development and that impact fields in the modern tech, where we are using this photoelectric effect concept and how we are depending on it. So if I significance of the photoelectric effect and summarize towards future, that it is basically gives us the photoelectric effect is a fundamental quantum phenomenon. It revolutionary physics, the Einstein's explanation. Yes, very obvious. It is the revolutionized of physics, technological advancement. It enabling us to used in various advanced technology in this effect, and it is very powerful in that, and there are several ongoing research and innovation for this with this photoelectric effect. So we can conclude it with a line that photoelectric effect remains significant. It continues to inspire ongoing research. It is a fundamental effect, an Einstein explanation, evolution of physics. It also enables numerous technological advancement. So it is a very powerful effect in the in physics and in our advancement in the technologies. Thank you.